Welcome to the Exam 2 review problems. This review, I timed myself, took me 1 hour and 2 minutes. So you might want to time yourself on problems and see how long it takes to do each problem. Okay, so ascorbic acid or vitamin C, when this was loaded into the software, we lost our subscript. So let's rewrite this. C6H8 oxygen 6 is an essential vitamin. Calculate the molar mass, grams per mole, of ascorbic acid. So the first thing we want to do is we want to see that we have 6 carbons times 12.011 gram per mole from the periodic table, plus we have 8 hydrogens, 8 times 1.008 grams per mole, plus we have 6 oxygen, 6 times 16.00 grams per mole. And when you add this up, I got 176.13 grams per mole for the molar mass. What amount of moles are in 225 milligrams of ascorbic acid? So that is our given. We start with that over 1. 225 milligrams of ascorbic acid, C6H8O6, over 1. And we're going to go from milligrams to grams to moles because it's asking for the moles. And to go from grams to moles, we're going to use the grams per mole molar mass. And if you remember, that was that big cursive M. Okay, so for 1,000 milligrams, we have 1 gram. And for 176.13 grams, we have 1 mole. And so then if we take 225, divide by 1,000, divide by 176.13, we get 1.28 times 10 to the third mole of ascorbic acid. Okay, the next question asks how many molecules are in this 225 milligram tablet. So since we already did this work and we have how many moles, we're just going to use Avogadro's number. So 1.28 times 10 to the third mole of C6H8O6. And for 1 mole, we have 6.022 times 10 to the 23rd molecules. When we put that in our calculator, we get 7.69 times 10 to the 20th molecules of C6H8O6. Okay, this question, what is the mass percentage of carbon in each of the following compounds? So we have caffeine, C8H10N4O2. Now, we wanted to do the part carbon over the whole of your molecule times 100%. So the part of the carbon, and that's grams per mole, the whole of the molecule is grams per mole. So we have C8, so 8 times 12.011 gram per mole of carbon, and then we have to do the formula mass of our molecule. So if you take 8 times 12.011 gram per mole, the carbon, plus 10 times 1.008 gram per mole for the hydrogen, plus 4 times 14.01 gram per mole for the nitrogen, plus 2 times 16 grams per mole for the oxygen, and you total that together, you should get 194.21 gram per mole. And you put this on the bottom, 194.21 gram per mole, times that by 100%. And when you do that, you should get 49.5% carbon. Okay, because this will 8 times 12 works out to be 96.088 grams per mole. Okay, you do the same thing for sucrose. So you're going to do 12 carbons over C12H22O11 times 100%. And that's going to simplify when you add 12 carbons plus 22 hydrogens and 11 oxygens. You should get 144.13 grams per mole over 342.31 grams per mole times 100%. And that works out to be 42.11%. Now remember, you have to show all your work here. Okay, the last one is ethanol. And ethanol is C2. Instead of H5, we're just going to go ahead and make that H6 oxygen. And that formula weight, that mass, would be 2 times 12.011 gram per mole plus 6 times 1.008 gram per mole plus 1 oxygen, 16 gram per mole. When you add all that up, you get 46.07 gram per mole. And you have 2 carbons, so it's 2 times 12.011 gram per mole divided by 46.07 gram per mole times 100%, and that works out to be 52.14% carbon. Okay, going to the next. We have a compound containing only sulfur and nitrogen, and it's 69.6% of sulfur by mass. So what you want to do here, if you remember, 1, we change percent to gram, and then we're going to convert gram to mole using the molar mass, and then we're going to divide by the lowest number of moles to get your subscript. So let's do that first, and that's going to give us our empirical formula. We have to get our empirical formula first. So let's see. So if we have 69.6% carbon, or sulfur, we make that grams of sulfur. And then we look at the periodic table and we see 32.066 grams for 1 mole of sulfur. And that gives us 2.17 mole of sulfur. Now, since there's only 2 compounds, what's the percent of nitrogen? Well, you do 100% minus 69.6%, because whatever's left has to be the other element, so 30.4% nitrogen. So we're going to convert that to grams, 30.4 grams. We're going to look at the periodic table and see that 14.01 grams for nitrogen for 1 mole of nitrogen, and that works out to be also 2.17 mole of nitrogen. So since 2.17, 2.17, you divide that both by 2.17, your empirical formula ends up being SN, sulfur nitrogen. Now, you're giving a molar mass 184 grams per mole. So that is of your molecular formula. So what you want to do is you want to take your molecular formula, molar mass, and divide by your empirical formula, molar mass. And that's going to give you your subscripts. Or it's actually going to give you a factor to multiply by your subscript. So so we have 184 grams per mole, and then our empirical formula would be obviously 32.066 grams plus 14.01 gram, and that works out to be 46.07 gram per mole. And when you divide that, you see that you get 3.99, which is 4. So you're going to multiply these little subscripts here, which you don't see because it's 1, and you're going to multiply by 4, so your answer is S4N4 for your molecular formula. Okay, this problem got cut off, but you have it, so we'll just go with it. We do have our balanced equation here, and it's a limiting reactant problem. So once again, here's these subscripts B5H9 and oxygen O2. Let's rewrite this balanced formula. 2 B5H9 liquid plus 12 oxygen gas yields 5 B2O3 and then plus 9 waters gas. So here's our problem, and it's a limiting reagent problem because you're giving amounts of both reactants. So you don't see this because it's cut off here, but it's 126 grams B5H9. We're going to put that over 1, and then you also have 192 grams of oxygen. And you're going to put that over 1, and then you can convert them both to moles of water because it asks for the amount of grams of water produced. So that's what we want. So we have to go to moles of water. So we're going to use the molar mass, and if you calculate that up, you'll see that 63.127 grams of B5H9 from the periodic table for 1 mole. And then we're going to use our coefficients in front of the borane compound in the water. So for 2 moles of B5H9, we have 9 moles of water. And when we put that in our calculator, we multiply and divide, we get 0.855 mole of water. And then we're going to do the next one with oxygen. Oxygen's molar mass is 32 grams per 1 mole of oxygen. Make sure you write your reactant. And then we see that we have a 12 in front of the oxygen. So for 12 mole of oxygen, we get 9 moles of water. And when we multiply that through and divide, we get 4.5 mole of water. So obviously, when we compare these, we see that 0.855 is less than 4.5. So then we need to convert mole of water into grams of water. So in order to do that, we just take our limiting reagent amount, 0.855 mole of water, and using the molar mass of water, which is 18 point, oh, I'm sorry. So let's see if we can erase that. Yeah, there we go. For 1 mole of water, we get the molar mass, which is 18.016 grams. We multiply that out, we get 15.4 grams of water. So be able to work a limiting reagent problem like that. Okay, this one's kind of cut off too. This reaction between potassium chlorate and red phosphorus takes place if you strike a match on the matchbox. We are reacting 52.9 grams of potassium chlorate with excess. You see that's excess? So if it says excess, then we know that the potassium chlorate is our limiting reactant. And we're going to do all of our calculations based on this compound, this reactant. So that saves us a step. What mass of P4O10 would be produced? Okay, so let's balance this equation. Potassium perchlorate plus P4 yields P4 O10 plus potassium chloride. Now, in order to balance these, you see that you have 3 oxygens on the reactant side and you have 10 on the product side, and the quickest way to do this is to go for an even number that can go both, some multiplier. So 3 and 10. So I'm going to go with 30. We're going to go with 30 oxygen. So I'm going to put a 10 in front of the potassium chlorate. I'm going to put a 3 in front of the P4O10. Then I'm going to count my oxygens. And I'm going to see that I'm just going to go ahead and count 10 potassiums, 10 chlorines, and 30 oxygens. And over here I have 12 potassiums and 30 oxygens. And so then I want the same number of potassiums here. So I'm going to put a 3 in front of the phosphorus, and then I'm going to put a 10 in front of the potassium chloride. And then I'm going to check. So that's 10 excuse me, potassiums and 10 chlorides. So we're good there, we're good there, we're good there. So everything looks good. So it's balanced. And now we can start with our given, which is the number with the unit. It's the only one in the problem. And we're going to start with that over 1. 52.9 grams of potassium chlorate, KClO3 over 1. And then we got to go to moles. So we're going to go from grams of potassium chlorate to 1 mole of potassium chlorate. And then we're going to go from mole of KClO3 to what it's asking for, which it wants, what's the mass? That's grams of P4O10. So we're going to go to mole of P4O10. You have to go to the mole-to-mole bridge, which is on the periodic table here, or on the balanced equation. So we have 10 coefficient in front of the potassium chlorate, and we have in front of the P4O10 we have 3. But we want grams, so we're going to have to go one more step, and for 1 mole of P4O10 we got to look at the periodic table and calculate its molar mass, and we see it's 283.88 grams. So see if you can get 283.88 grams. And then the molar mass here for potassium chlorate is 122.55 grams. And so when you take 52.9 divided by 122.55 times 3 divided by 10 times 283.88, you should get 36.8 grams of P4O10 produced. And that is the answer for this problem. Okay, the next problem, we need to calculate the molarity. So molarity is moles of solute, remember the little guy, over 1 liter of solution. And so the first one is 5.623 grams of sodium bicarbonate in 250.0 milliliter solution. And I just write SOL for that. Okay, SOLN. Okay, so 5.623 grams of sodium bicarbonate. We got to convert that to moles. So 84.019 grams. That's its molecular mass for 1 mole of sodium bicarbonate, and that gives you 0.0669 moles. And then you have 250 milliliters, and we got to get this into liters. So for 1,000 milliliters, you have 1 liter. That's 0.2500 liters. So now you're going to take 0.0669 moles of sodium bicarbonate You're going to divide by 0.2500 liters, and that is going to give you a concentration of 0.2677 molality, sodium bicarbonate. Now, make sure that you have 4 significant figures here. Okay, so check your significant figures. Okay, the next problem is 184.6 milligrams of potassium chromate, K2Cr2O7. And we're going to convert that to moles, so 1,000 milligrams per 1 gram. And if you go to the periodic table and you add up 2 potassiums, 2 chromium, 7 oxygens, you should get 294.19 grams of potassium chromate for 1 mole of K2Cr2O7. And that works out to be 0.6275 mole of K2Cr2. Is that milligram? I did gram. Alright, well, I'm going to change this to gram. So, I'm not sure. So, this is gram, and we're not going to do that. So, this, if you change that to grams instead of milligrams, you get this number, and we're in 500 milliliters of solution, which if you convert that, that's 0.5000 liters. So now you take 0.6275 mole of K2Cr2O7 divided by 0.5 liter, you get 1.255 molar K2Cr2O7. Make sure that you have 4 significant figures there. And the last problem I have is 75.0 milliliters of ethanol. So now we have the density, and density is 0.79 grams equals 1 centimeters cubed. And we also know that 1 centimeters cubed equals 1 milliliter. So we can go, we can say 0.79 grams per 1 centimeters cubed. And for 1 centimeter cubed, we have 1 milliliter. That works out to be 0.79 grams per milliliter because these cancel out. And then we can go back up here and go 75 milliliters of ethanol, which is alcohol people drink. You have 0.79 grams per 1. Oh, I'm sorry. Got this backwards, don't I? Okay. So ethanol. So we need milliliters on the bottom. So for 1 milliliter, we have 0.79 grams. And then we use this molecular weight, which if you look on the periodic table, you'll calculate 46.07 grams per 1 mole. And then that works out to be 1.286 mole of ethanol. And then we are putting this in a 250 milliliter solution. So we got to convert that to liters. So for 1,000 milliliters, we have 1 liter. That works out to be 0.2500 liter. And now we're just going to divide the moles over the liters. So we're going to divide 1.286 moles of ethanol divided by 0.2500 liters, and that is going to give us our concentration of ethanol in this solution, and it works out to be 5.144 molar ethanol. Make sure that you have 4 significant figures because that's what you have in the problem. Okay, this problem says calculate the concentration of sodium ions present in 2.5 mole solution of sodium Na2SO4, sodium sulfate. Okay, so what we need to do is we need to go from, you need to see that for 1 mole of Na2SO4, we have 2 moles of sodium ions. Okay, so then we start with our given, which is the number with the unit here, and we go ahead and say 2.5 mole of Na2SO4, and notice we want concentration of sodium ions. Concentration means M. Molarity, so we need mole of sodium ions divided by liter of solution. So we need to get the moles of sodium ions. So we have moles of sodium sulfate, and then for 1 mole of sodium sulfate, we have 2 moles of sodium ion. And this works out to be 5.0 mole of sodium ion. We have 2 significant figures there, so we keep 2 significant figures. And then we basically just take 5.0 mole of your sodium ions, and you're going to divide this by 1.25 liter solution, and that's going to be 4.0 big M, okay, of sodium ion. I just put aqueous because it's in water. Okay, the next problem we have is writing balanced molecular formulas, ionic formulas, and net ionic formulas. And then for the first two, we're going to calculate the mass of each product. So we're going to look for a solid that's produced, and we're going to calculate the grams of that. And then for problems C and D, we're going to calculate the volume of acid or base that's needed at the equivalence point. Be able to do this, recognize that it's an acid-base reaction, and be able to calculate that volume for your exam on Monday. So let's look at the first one. The first one is aluminum nitrate, NO3, 3, this is aqueous, plus KOH, aqueous. We're going to try to write this molecular formula, balanced molecular formula reaction. And what I do go ahead and do, I just go ahead and break these up and start writing also my ionic formula. So aluminum is a 3+ charge here, and you can determine that because your nitrate, you have 3 nitrates. Each one of them is a 1-. And then we go ahead and break up the potassium, and then we have an OH-. Now notice I haven't balanced this yet, but the reason why I want to do this is because in solution, the aluminum is going to pair with the hydroxide. Now I want to go ahead and figure out what my charge is. So we have a 3+ for aluminum and an OH-. So I'm going to need 3 of those to make it sum 0. And at this point, I don't know. I have to apply my solubility rules to figure out what's going to go into that phase bracket, parentheses. And the next one I'm going to pair is potassium with nitrate, and I see that's 1+ and a 1- charge. And I know anytime I write potassium or nitrate, that is an aqueous. I don't even have to think about it. So I'm going to apply my solubility rules for hydroxides, and I see that hydroxide is with aluminum, so this is going to be a solid. Okay, now I'm going to balance my equation, and I see that I have 1 aluminum, I have 3 hydroxides, so I'm going to put a 3 here, make that red, 3 potassium, so I'm going to put a 3 here, 3 nitrates, 3 aluminums. Okay, so by adding the 3 there, but I'm going to go down here too, so I can get points on my ionic formula and put a 3 here in front of the potassium, 3 in front of the hydroxide, and I'm going to finish writing this equation. So the products now go to aluminum hydroxide, and we're going to keep that as a solid, so we don't break that up. But then we need to break this up in 3 potassium ions plus 3 nitrate ions. And that's exactly what happens in solution. Now the next part of the question is the net ionic equation. And when I do this, I need to um, cross out any of my spectator ions. And you notice it's going to be whatever goes into the solid. So I'm going to keep aluminum, and I'm going to keep hydroxide. So my spectator ions will be the nitrate and the potassium. So when I rewrite this, I just write aluminum 3 plus aqueous plus 3 hydroxides aqueous goes to aluminum hydroxide solid. That's my net ionic. And then my problem is a limiting reagent problem because I have the milliliters and the molarity of each one of these reactants. So that gives me the moles of each. I'm going to go from the moles of each to the moles of the aluminum hydroxide product. So we just basically go from 50 milliliters, and we use molarity, which is 0.200 moles equals 1,000 milliliters. So for 1,000 milliliters, I have 0.200 mole of aluminum nitrate here. And I look at my balanced equation, for 1 mole of aluminum nitrate, I have 1 mole of aluminum hydroxide. Okay, and then that works out to be 0.01 mole of aluminum hydroxide. So then I have to do the same with the next amount. So 200 milliliters of barium chloride, and its molarity. So 1,000 milliliters of barium chloride, I have 0.100 mole of barium chloride. And then using the coefficients in front of, oh, I'm sorry, it's not barium chloride. It is potassium hydroxide. So let's do that. Is that right? 200 milliliters, yes, potassium hydroxide. And then for 3 moles of KOH, we have 1 mole of aluminum hydroxide. And that works out to be 0.0067 moles of aluminum hydroxide. So when we compare these two, 0.01 and 0.006, this is the smaller. So that is my limiting reagent. And so this is my limiting reagent, and it asks for how much. So I'm going to do my next reaction based on that amount, which ends up being 0.0067 mole of aluminum hydroxide. And I use its molar mass to find out that 1 mole of aluminum hydroxide, we have 77.98 grams of aluminum hydroxide. And that works out to be 0.522 grams, and we need 3 significant figures. So that is the answer for problem number A. And then we go to the next one, which is problem number B. First thing we do always on these is we write our balanced equation. Okay, so now on part B, we want to always write our balanced equation. So we have barium chloride aqueous plus iron sulfate aqueous. And then we have to predict the products, so we're coming down here and we break them up into their charges. Barium is a 2+, it's in group 2A. We have 2, the big 2 here, chlorides with a 1- charge. We have 2 irons because of the subscript 2, and this iron here should have a 3 there. Should be a 3+ charge. You see that there's 3 sulfates, so that's how we know. Sulfates is a 2-, and there are 3 of those. So if you total that up, 3, -2, that's -6, and then iron plus 3 and 2, that's +6. Okay, so now barium is going to combine with sulfate, and so and they have a +2 and a -2 charge, so we don't have to do anything there, it's just barium sulfate. And we're going to have to figure out what we put in that parentheses based on its phase, whether it precipitates or not, whether it's soluble or aqueous. And then we're going to combine iron with chloride, and we have a 3+, so we're going to need 3 chlorides. And this is going to be aqueous because it's a chloride and it's not a halide with silver or mercury or lead. And then barium sulfate is a solid. So if you look at your rules there, sulfates are usually soluble unless they're with certain other compounds. Okay, elements. Okay, so now we want to balance these equations. So we have 1 sulfate, we have 3 sulfates. We're going to have to put a 3 here in front of this. So 3 sulfates now. We have 3 bariums, so let's put a 3 over here. We have 6 chlorides, so let's put a big 2 there. And we have 2 irons. So that balances it. So let's come down here to our ionic equation and make sure we get these as well. So we have 3 bariums now. We have, so this, we scratch out 3 times 2 there, so we get 6 chlorides. We get still 2 irons, 3 sulfates, and then our product we're going to keep the barium together, barium sulfate, because it's a solid in our ionic equation. And then our ions are 2 iron, 3+ aqueous, and 6 chlorides, aqueous. So that's our balanced ionic equation. And so for our net ionic, we're going to cross out our spectator ions. Now notice the solids are going to stay together. So sulfate's going to stay and barium's going to stay. So chlorides on both sides, that's going to go. Iron's going to go, and then when we rewrite what's left over, we have 3 barium, 2+ aqueous, plus 3 sulfates, 2- aqueous, and that goes to 3 barium, sulfates, solid. And that is your balanced net ionic equation with all its phases. And then the next thing you're supposed to do is figure out how much product of this barium sulfate is produced. So this is a limiting reagent problem, so we have 100 milliliters of barium chloride. Okay, and then we have, for 1,000 milliliters of barium chloride, we have 0.100 mole because of the concentration of barium chloride. And then we're going to look at our balanced equation, and we're going to see that for 3 mole of barium chloride, we get 3 mole of barium sulfate. And that works out to be 0.01 mole of barium sulfate. We do the next problem, and the next one is for 100 milliliters of iron sulfate, Fe2SO43. The concentration is 1,000 milliliters. We have 0.100 mole of iron sulfate. And then we look at the balanced equation, and we see that for 1 mole of iron sulfate, we have 3 moles of barium sulfate. So for 1 mole of iron sulfate, we have 3 moles of barium sulfate. And then when we multiply that and divide that through, we get 0.03 mole of barium sulfate. So our limiting reagent would be the 0.01 barium chloride, because that 0.01 mole is less than 0.03 mole. So then we take the 0.01 mole of our barium sulfate, the limiting reagent amount, and we use the molar mass for 1 mole of barium sulfate. We look on the periodic table and we get its molar mass to be 233.39 grams, and that ends up being 2.33 grams of barium sulfate that is produced in this reaction. Okay, the next problem is an acid-base reaction. So you need to be able to do these titration problems. You should recognize that sodium hydroxide is a strong base and that nitric acid is a strong acid. So when you have a strong acid and a strong base, you end up getting, what happens is the sodium, let's break them up into charges. Sodium breaks up into its ions, hydroxide breaks up into its ions, the acid breaks up into H+, and then nitrate breaks up into its anion. And then, just like we did in the precipitation problem, the sodium and the nitrate come together. And since it's a +1 charge, and this is aqueous, and then the hydroxide and the acid come together, and this is going to make a liquid, so H2O liquid. So then go ahead and finish writing your ionic equation. Since sodium nitrate is aqueous, we break those up into its ions, and we keep water together because it's a liquid. And is this balanced? We have 1 sodium, 1 nitrate, 2 hydrogens. Yes, so it's balanced. So we don't have to worry about putting coefficients in there. And then the next thing we want to do is our net ionic equation. And basically we're going to keep everything together that makes the H2O liquid, okay, because it's an L. So you keep your solids and your liquids or your gases. So we're going to keep the OH, and we're going to keep the hydrogen. And we're going to cross out our spectator ions, which are on both sides, the sodium, and then the nitrate. So we write our net ionic equation as OH minus, and it doesn't matter what you write first, plus H plus aqueous yields water, liquid. So that's basically what happens when you add a strong acid and a strong base. You're making water. And in this problem, it asks for the amount, the volume of acid needed at the equivalence point. So basically you're going to start with, you're going to get the moles of your base, and you're going to use the mole to mole bridge to get the mole of your nitric acid, and you're going to use the molarity to get your volume in milliliters. So this, you're going to use molarity that's provided, and this, you're going to use your coefficients from your balanced equation. And how do you get the moles of sodium hydroxide? Well, you're given milliliters and molarity, so you can combine these two to get the moles. So let's do that. So you have 50.0 milliliters of sodium hydroxide. You put that over 1. Then you use the molarity. So for 1,000 milliliters, you get 0.200 mole of sodium hydroxide. And that's in that 0.200 molar. That's what that means. 0.200 mole equal 1,000 milliliters. Now you go from mole of sodium hydroxide to mole of nitric acid, because it asks for the volume of nitric acid. You got to go to your mole to mole bridge. You look at your coefficients and you see that for 1 mole of sodium hydroxide, we react with 1 mole of nitric acid. And now we use our molarity that is provided in our problem, and we see that for 0.150 mole of nitric acid, we have 1,000 milliliters of nitric acid. And this was in our molarity of 0.150 big M for HNO3, which we use as a conversion factor of 0.150 mole of HNO3 to equal 1,000 milliliters. So when we put this in our calculator, we get 66.7 milliliters of nitric acid, and that is what is needed to reach an equivalence point. You can see that these cancel out: milliliters of sodium hydroxide, moles of sodium hydroxide, moles of nitric acid, to leave you with milliliters of nitric acid. Okay, you're going to do this problem again for part D. So this is 8D. You have a strong base. You have calcium hydroxide. So your bases are hydroxide with metals. So this strong base is a strong electrolyte. And then we have nitric acid, HNO3, strong acid again. And let's go ahead and break up our ions so that we can write our ionic equation. We're going to have 2 OH minuses here. We're going to have 1 H plus, and we're going to have a nitric acid here. Okay, and then we're going to pair the calcium with the nitrate. And to get this to sum 0, we're going to need 2 nitrates, so we're going to have the parentheses. A lot of people don't get that here. We have to have parentheses when we have these polyatomics. We need more than one of them. And this is going to be aqueous. You see that a nitrate is soluble. And then we are left with H2 and O. All right, we're going to make water, H2O, liquid. Now we are going to look to see what our coefficients are needed to balance. We see that we need 3 nitrates. So there's 3. Wait a minute. We don't need 3. That's wrong. We need 2, right? Did y'all catch that? Because calcium's a 2 plus charge. And so this is going to be a 2 here, and then we're going to need 2 waters. So let's make sure over here we balance it with 2 H pluses and 2 nitrates. And then this goes to calcium. Oh, no, we got to break that into our charges. So calcium 2 plus 2 nitrates plus 2 waters. Now to make our net ionic equation, our net ionic, we have 2 waters and we have hydroxide and H plus. Everything else is spectator ions, calcium 2 plus, 2 nitrates. So we rewrite this as 2OH minus aqueous plus 2H plus aqueous yields 2H2O, and we make a liquid there. And then in our problem, we are given amounts, and it asks for the volume, at this time the base needed. Okay, and we're given molarity of 0.05 molar HNO3, and we're also given 0.0200, let me get all my molar calcium hydroxide solution. So go ahead and make these into conversion factors. 0.0500 mole of HNO3, and since we're dealing with milliliters, just make that a 1,000 milliliters instead of 1 liter. Make your life easier. And then over here, 0.0200 mole of calcium hydroxide equals 1,000 milliliters of calcium hydroxide. Now, the given, we start with 35.00 milliliters of HNO3 over 1, and we use this conversion factor here, molarity, the big M, 1,000 milliliters of HNO3. We have 0.0500 mole of HNO3 And then we look and we see up here in our molecular equation for 2 mole of HNO3, we have 2 moles of water. Oh, I'm sorry. We were going to the volume. Sorry. Okay. Wait, we want to go from moles. So for 2 moles of HNO3, we have 1 mole of calcium hydroxide, and for 0.0200 mole of calcium hydroxide, we have 1,000 milliliters of calcium hydroxide. When you put that in your calculator, you should get 43.75 milliliters of calcium hydroxide needed to titrate that. Okay, this is similar to the problems we worked on Friday, and you can read that in your book. These are oxidation states for all atoms. So there's the oxidation rules, and you just primarily follow those, and then you figure out the oxidation states for each element within a compound. So some of your rules state that oxygen is usually a -2. Your group 1 and group 2 are +1 and +2. And fluorine is always a 1-. And so let's just start with Na4Fe. Oh no, let's start with the first one. Potassium permanganate. Okay, so if oxygen is a -2 and there's 4 of them, that's a -8, and potassium is a +1, then what is manganese? Because this has to sum to 0 because there's no charge. So then you would just do +1 plus manganese plus -8 equals Mn equals 8 minus 1 Mn. There's only one of them, so a +7. Okay, the next compound is Na4 iron OH6. And here you can just keep your hydroxide together if you want. So OH is -1, and there's 6 of them, so it's -6. Here you have 4 times +1 for sodium, so that's +4. And then iron you don't know, so +4 plus iron plus a -6 sums to 0. And iron equals 6 minus 4. Iron equals a +2. And if you went and made every oxygen -2 and your hydrogen's a +1, you would have gotten the same answer. Okay, so now for SF4, fluorine is a -1, and there's 4 of them, so that's fluorine equals a -4. Well, sulfur plus -4 equals 0. Sulfur equals a +4 here, oxidation state. Okay, and then we have, just checking that, okay. Okay, one more. HASO2. O2, oxygen is 2 times a -2, so that's a -4. Hydrogen is a +1, so we have +1 plus AS minus 4 equals 0. AS equals 4 minus 1. AS equals a +3 oxidation state. Be able to do that on the exam tomorrow, and then or Monday. Identify the oxidizing agent, reducing agent, substance being oxidized, and substance being reduced in the following. Show the oxidation states of each element. Okay, there's actually 2 here, but you don't see the other one. We'll just go ahead and rewrite these. SiCl4 liquid plus 2 magnesium solid goes to 2 magnesium chloride solid plus silica solid. Now, you have your rules, apply your rules. So when we see these elements in their by themselves in their elemental state, we sign oxidation of 0. So silica, and then I just go and find silica. So silica here, match it with here. Silica tetrachloride there would be in an oxidation state of a +4, because chloride would be a -1, and there's 4 of them, right? So when you go, and then you can find the other one, magnesium here, and when it's in a compound, it is, since chloride is a -1 and there's 2, that's going to give this a magnesium a +2. So when you go on the scale of 0 to a +2, you're increasing. When you're increasing, that's oxidation. So you're increasing the oxidation number. That's oxidation, and that is your reducing agent. And then for silica, you could see that you're going from a +4 down to a 0. So this is a reduction in the oxidation state. So that's reduction, and you can call that your oxidizing agent. And if you did this, that would be full credit. And if you have a question worth 10 or 15 points, and you do it like this, you'll get all your points. Okay, the other problem that's given to you, equation here, we'll rewrite it: zinc solid plus 2 HCl aqueous goes to zinc chloride aqueous plus hydrogen gas. So you find your elements in their elemental state. So zinc is a solid there, it's 0, hydrogen is 0, and then you match up your zinc from your reactant side to the product side, and here you see that it's a, this should be a 2 there, so your chlorine is a -1 times 2, so that's -2, so your zinc should be a +2, and then you come over here and you do your hydrogen, and once again, chlorine is a -1, hydrogen would then be a +1, and so then you think about this, if you go from a +1 to a 0, that's decreasing, so that would be reduction, and you can just go ahead and write that that's the oxidizing agent. And then here's zinc is going from a 0 to a +2, that's an increase, so that's oxidation, and that would therefore be your reducing agent. There you go. So check your work and get those problems turned in.